you for that introduction. So I'm really excited to be sharing this work with you today. This work is part of a project that is still ongoing. I'm in the later ends of the analysis phase, so I will greatly appreciate any feedback or suggestions that people have at the end or in the chat. As evidenced by the fact that we are all here, labs are a big topic right now. Specifically the question of, why and how do we teach students to do labs? This importance of this question is underscored by the accumulating evidence that our current teaching practices regarding labs might not be as efficacious as we originally thought they were, as well as the reality that labs are hazardous. All the photos on this slide, by the way, are mine. They're time consuming to set up and to do as a student. They're expensive. So forget the chemical hazards. Let's talk about the fume hoods needed to contain disasters like this on the screen. I didn't cause this, but I took the picture. Fume hoods are incredibly expensive to install and to operate. The chemical byproducts are environmentally harmful. It can be a stressful experience. Many students find labs to be exciting, but many also find them to be stressful. And it inherently excludes certain students. So try to imagine being a student in a wheelchair working at that fume hood. So fundamentally, though, when we come back to the question of why do we teach students to do labs, the answer is because much of chemistry happens in labs and many chemists work in labs. But there's definitely room for improvement in how we use labs as a teaching environment and how we address challenges. So as a result of the fact that we're recognizing that there are issues with prescriptive cookbook labs, there's an increasing movement to move to reforming lab courses. People are using inquiry labs, student driven research projects, as well as technology like LearnSci to model lab activities. And so this is great, fantastic. However, I do question whether we might be jumping a little bit ahead of ourselves. So as a lead fellow at the Chicago Center for Teaching, one of my roles is to help other instructors improve the effectiveness of their teaching. And that often centers around a discussion of backward design. So if you're going to build a course, you need to start from figuring out what the desired outcomes are. And the last step is to plan out the teaching strategies, planning the student experiences. And so while I would say that there's been a lot of work done in understanding, how the objectives for, helping students through a research process or understanding the nature of science, I question whether we have really identified what the goal is in terms of what types of hands-on skills students need to be learning. For example, manual titrations using a burette are super common in Gen Chem labs. I have never used one in research. I've never seen someone use one. I'm sure somebody out there uses it, but frankly, it would have been a lot more useful for me and my colleagues to have learned how to use a shlink line. So I just, I'm not saying we should all run out and go buy shlink lines immediately, but I do think that we need to seriously question, whether we've identified the right outcomes in terms of hands-on lab skills. So what I propose essentially is that in order for us to develop really effective curricula, we need to be looking at what are students doing downstream in their careers, in authentic bench environments. What are they doing there? And if we can identify that, then we can look backward and say, okay, so what do we need to teach them to do? And so this is just examples of types of questions that I think that we should be trying to address here. What type of equipments do they use, or what techniques do people need to be able to do? And in helping students prepare to carry out those techniques, we're helping them for job market relevancy and making sure that they're getting impactful experiences. So just to sum this all up, in order to effectively design next generation lab courses, we really need a shared empirical understanding for what that end product should look like in the first place. So the question from my project here is I wanted to go into an authentic, working chemistry lab and ask how are those chemists using their skills, their hands-on psychomotor skills to conduct their bench research. And so this took the format of phenomenological grounded theory case studies. So I went in, I used action cameras on their participants' heads to get a first-person view of what's happening, what are they experiencing, and then analyze that through the emergent themes. So this was naturalistic data collection coupled with retrospective interviews. So asking the participants to provide additional context about that observational data. I also, as part of this study, also gathered information about their educational history and how they developed those skills that they used, but I don't have the time to go into that today, but that is a great discussion for a future time. I decided I wanted to focus specifically on synthetic chemists because they are very bench intensive field of chemistry. It's also my personal specialty. So I'm going to be analyzing what people are doing in the lab. I need to actually be able to recognize equipment. So I picked the field that I could do this work in. And specifically, I focus on growing and recruiting academic graduate students, partly because I felt that industrial labs were never going to let me into their lab spaces due to insurance issues. So I sought out grad students working in synthetic chemistry instead. So each participant did 2-hour sessions where they were recording their work while they were working in their lab on their projects. I coded those recordings. The first recording I analyzed that with grounded theory to establish my framework, and I analyzed all the remaining recordings using that framework. Afterward, we had the retrospective interview where I had them clarify some segments that I wasn't exactly sure what they were doing or why they were doing it. And they also coded part of the recording as well to help as a sort of validation strategy to make sure I was coding appropriately. They did this process several times. And then at the very end, we also had an interview, which again, I'm not going into today. Would be happy to talk about further in the future, where we talked about how they developed those skills. So overall, what I'm going for here is using both a naturalistic observation approach, but also using the participant and using them as a validation strategy for this phenomenology. So this is the camera and the other equipment. Thank you to LearnSci for providing the funds for this. As a broke grad student, I could not do this myself. And then this is what you see through the camera. It gives fantastic clarity. You can see everything they're doing with their hands very, very well. And then afterwards, I was able to project those images up onto a screen so that they could see that as well during the interview. I ended up being able to recruit 2 second-year PhD students. It was harder to find people who wanted to do this than I thought. First off, because people are shy about being recorded, but secondly, because I was doing this during COVID. So we had to very carefully time our recording sessions to go, between the surges, unfortunately. They both identified as organic chemistry methodology students, and they were working pretty much by themselves. I do think it's important to note that I didn't know them or their work at all, so that didn't factor into my coding. Everything was based off the data, not any pre-existing knowledge. And they had pretty standard backgrounds for American PhD students. So the coding started off with a basic level of coding what I called meaningful actions. So a meaningful action is something that is a specific physical action that they did related to accomplishing a task while they're in the lab. And so there were 3 categories that emerged for how to sort meaningful actions. I'll talk a bit more about that in a moment, but essentially I sorted every action into an equipment, a technique, and a purpose category. So here are some examples of meaningful actions and what doesn't qualify as a meaningful action. So placing a spatula down really carefully to avoid contaminating the tip. That's a meaningful action. But if you're just putting it down, you're just putting it down because they're done with it. That's not meaningful. That doesn't say anything about their skills and how they're using them to accomplish something. In all, there were about 11 hours of recording, and about 7 hours were be able to code it as a meaningful action. So sometimes they were just waiting around. Sometimes they were doing something that wasn't meaningful. So roughly half-ish of that time period was meaningful actions. So here are the categories that each action got sorted into. So the equipment is the what. What are they working with? The technique is how. What's the sequence of events that they are doing in order to accomplish something? And the purpose is the why. What's the objective at the end of the day? So there are 32 types of equipment. This range from things like columns, syringes, which were I classified as like a transfer tool. They're transferring a liquid, and also the human body. They use their body as a tool. They use their hand to warm things. They use their hand to smack things and make sure that chemicals fell off from one spot into another. So they actually use their body a lot as a tool itself. There are 30 types of technique. things like thin layer chromatography, transferring mass in air-free environments. And then 14 types of purposes. Now 6 types of purposes actually had subcategories that I call optimized time and effort. So there were 6 categories of purposes where they spent a lot of time trying to save time. So they might be doing something to avoid contamination, and then they also employed a little trick to make it easier or faster to avoid contamination. So I classified that as its own category as well. These little tips and tricks to be efficient. So here's a screenshot of one of the participants working at the automated column. So they're labeling their column's name in the computer to keep track of the conditions. So this here is how I coded it. Now this is different from when later on their column was leaking. And so they paused the computer so that they could fix the leaky condition. Same equipment, same technique, but different purpose now, because the reason that they're stopping the computer to fix the leak is that they don't want to lose material, versus the reason that they're labeling their column is so that they can keep good records, so that they can go back and see what they did again. And then here's some examples of the differences between, the example of purified product purpose versus optimizing time and effort while purifying product. Essentially, if you have to run the column to purify the product, but as you then go and adjust the conditions to make it happen faster because you just want to hurry this thing up, that's optimizing time and effort there. Now, Interrater reliability is an extremely difficult and questionable thing to do with naturalistic video data because a lot of the codes overlap. So I'm just kind of providing you here with kind of a visual example of how our coding is related. But essentially during the interview afterward, I had the participants verbally say out loud when they thought they were doing a meaningful action. And you can see here that there's a shocking degree of overlap. I was actually surprised at how often we agreed on what was meaningful and what they were doing and why they were doing it. And then here's the other participant as well. Again, some fantastic overlap. So I took this as a sign, not only that was I coding reliably, but I was using them as validation as well, because they're the ones doing it. So they should have a good idea as to whether it's a meaningful action and what they're doing. So I use this as a validation strategy as well. Overall, I was able to identify almost all of the actions and the reasons for the actions myself, but there were 100 codes, which is about less than half an hour, at which I had to ask them, can you tell me what you're doing? Or can you tell me why you're doing what you're doing? So here is the overview of the codes in the equipment category. I've color coded them just to, not scientifically, but just to kind of help you get an overview. There are things like the shrink line, they used a heat gun, they used personal protective equipment. If we sort them according to how often they use them and the percentage of time when they were doing meaningful actions, what we see is that 40% of the time, they are just transferring mass. They're moving chemical A to chemical B. That was a bit surprising to me that much of their time is taken up by them using just spatulas and syringes. Techniques, they have things like liquid extraction, preparing NMR samples, using a sonicator, cleaning up. Rotatory evaporation took the most time, followed closely by cleaning and thin layer chromatography. We also see that laboratory and workspace management is something they did a lot. So a lot of like moving things around, prepping things, even though it didn't take much time. And then purposes. I find this slide very interesting. So they have a variety of purposes that they were trying to accomplish. And some of them were solidly related to the experimental goals. So synthesize that product, purify that product, and analyze the results. But they also have a set of purposes that are related to things that I label as defensive. So they had a series of actions that they undertook to protect their own like mental state. So to take something that was really annoying them and to deal with it, or to make it so that their lab mates don't get annoyed by something. So I classify these as defensive categories here. Overwhelmingly, the thing that they spent the most time on individually was avoiding contamination and purifying the product. They didn't spend that much time on things like synthesizing the product. It's overwhelmingly about purity. And then if you take and you look at just all of the optimization categories and you add them together, they're spending about 25% of their time just using little tips and tricks to save themselves time. So I think it was interesting when we heard earlier today that students are focusing in lab classes on efficiency. I question whether we should really be looking at that in a negative view, because what we see here is that in the graduate lab, they're focusing on efficiency too. And that's not a bad thing. Time is a precious resource. So maybe we should be hoping that our students are efficient while also paying attention to what they're learning. Here's just one example. I just want to walk you through just an example of some crosstabs data. So you can see that some equipment, techniques, and purposes.
Hi, Elizabeth. Sorry, we really got to get back on schedule. Can you kind of wrap up in a minute or so?
Okay, sure.
Thank you.
Okay, so I did cluster analysis to try to determine essentially do like what are the relationships between the equipment, techniques, and purposes. And I guess since I'm being cut 5 minutes short, I'll just go to my main takeaways. Overall, these participants are highly productive, they're highly skilled and efficient, and they value these skills that they use greatly. So they believe that these skills are extremely important to have when you enter grad school in order to be successful. The purposes that they are trying to achieve can be really viewed in terms of achieving experimental goals, ensuring reproducibility, and defending their existing resources. Some of their equipment and techniques and purposes overlap a lot with other techniques and purposes, but some of them are really exclusionary, only used, like some equipment is only used for one specific technique or one specific purpose. The most frequently used types of equipment are centered around transferring mass from point A to point B. Most frequently used types of techniques are about purification, analysis, record keeping, and cleaning up. And then the most frequently sought after purposes were avoiding contamination, purifying mixtures, and saving time and effort as well. So with that, I'd like to go ahead and thank my funders and of course the participants. So LearnSci helped provide grant support for this study, as well as National Science Foundation and the Chicago Center for Teaching. And I'll be happy to answer any questions in the chat.